Okay, so it's my pleasure to have Tess Bouis from Orsay, who's going to tell us about Motivic Cohomology of mixed characteristic schemes. Yes.
Thank you first for this invitation. I'm glad to be here. I'd like to tell you about Motivic Cohomology. First, let me recall what I mean by Motivic Cohomology. So this will take the form of a theorem. I mean to explain the Motivic Cohomology is a smooth case. So this is work due to many people, but in particular, Davidson, Bloch, Ludin, Lichtenbaum, Vygotsky. And culminating in 2000. Okay, so it states the following. For any smooth scheme X, either of a field or in mixed characteristic of a Dedekind domain. Okay, so there are block cycle complexes. Which will be the complexes representing a theory of Motivic cohomology. So they are denoted like that. E I of X. Here the bullet stands for the cohomological degree. So it is a complex defined in terms of algebraic cycles on X. So more precisely, it is a dot minus I codimensional cycles. X times some simplex of dimension dot minus 2I. And you assume that these algebraic cycles intersect properly. They intersect properly the faces, so the faces being defined by this simplex. Okay. And you also take the differential for that, which is defined as the alternative sum of the differentials induced by this simplex. Okay. So this is defined in terms of algebraic cycles, and we'll see that as an object, the Dirac category of abelian groups, so the Dirac category of Z, is indexed by a non-negative integer I. Okay, so this will be a theory of Motivic cohomology. These are Motivic complexes, and we are really interested in the Motivic cohomology groups of X, which are defined as the cohomology groups of these complexes. Okay. More precisely, the main property we expect for Motivic cohomology is to be related to algebraic K-theory. So more precisely, there's natural Atiyah-Hirzebruch spectral sequence defined on the P2 page by the Motivic cohomology groups of X. Converging to the algebraic K groups of X. So said another way, Motivic cohomology is a refinement of algebraic K theory. So now these Motivic complexes are defined in terms of algebraic cycles and are in general really hard to compute. So one of the main tools to compute that is the following. So moreover, for any prime L, there is a natural comparison map called the Davidson-Lichtenbaum comparison map. Which goes from Motivic cohomology. So it's block cycle complexes. So ZIX minus UI. So we take a modulo L, modulo this prime number L, and to the étal cohomology of the generic fiber of the L-adic generic fiber of X. Okay, so we have a comparison map like that in any case. The result is that the fiber of this comparison map is in degrees at least I plus 1. L is non-zero in X. Okay, so there are really two results in this result. The first one is the case when L is invertible in X, in which case this is really in comparison in low degrees between the Motivic cohomology of X and the étal cohomology of X. The other case is when L is non-zero but not invertible in X, in which case this map factors with the map from Motivic cohomology of X, Motivic cohomology of X with L inverted, and then the previous map. Okay, we have comparison like that, which means that this is an isomorphism in degrees less than I, and is injective in degree I. Okay, so this is the end of the first theorem. So now the goal for today is to extend this theory, so extend Motivic cohomology, to non-smooth schemes. Okay, so
What does that mean? Smooth schemes.
I will say that in 30 seconds.
Okay.
Okay, so what I mean by non-smooth, I need to say for which kind of schemes I want to theory, and this is for maybe less than 30. So for any quasi-compact, quasi-separated scheme X, so in particular for any affine scheme and non-Noetherian in general, there are Motivic complexes which takes the place of these block cycle complexes, but with the definition which is not in terms of algebraic cycles. Again, we see that as an object of the derived category of abelian groups and indexed by a non-negative integer I. Okay. Then we have the main property for these complexes is the relation to algebraic K theory. Similarly, we have a natural Atiyah-Hirzebruch spectral sequence. Which looks the same as the previous one. So, going from the Motivic cohomology groups of X. The algebraic K theory of X. And here, this is really the non-connective algebraic K theory. In particular, you can see the information on the negative K groups of X. In the smooth case, the negative K groups are 0, and so you don't have information like that. Okay, so now we like also a Bell-Insulation non-comparison map. So we have that. So for any prime L, the natural Bell-Insulation non-comparison map. And it goes with the Motivic cohomology X modulo L to the étal cohomology X with L inverted. And for now, let me just take the result, which is slightly weaker than the previous one. So we have the control of this comparison map to étale cohomology. So it's fiber. We at least I plus 1. So if L now is invisible in X. Okay, so we do have a comparison map in general. When L is invisible, we have the same result as before. And when L is non-zero but not invisible in X, so in mixed characteristic, I will say more later in the talk. Okay, so we have that, and now we like also a comparison to the classical theory. So in the classical theory, it was implicitly used that the K-theory of X was A1 invariant in the smooth case, in order to use A1 homotopy theory. And here, so if compared to the classical theory, we have the following result. So if X is smooth over the Dedekind domain, so for instance, smooth over Z, if you enforce A1 invariance, so this denotes A1 localization on these Motivic complexes, then it gives you back the classical theory of block cycle complexes. Okay. Any questions so far? But, yeah.
If L is not invertible in X,
I will.
Yes. do you know that there's no negative Motivic cohomology? So do you know that the Bayesian Soleil
No.
balancing?
No. Okay, let me make a few remarks now. So this theory is related to several recent works. So the first one is the recent work of Elmanto-Morrow. So the first theorem, so theorem A, is due to Elmanto-Morrow. In equicharacteristic, i.e. for schemes over the field. So this is really an extension in mixed characteristic of this work. Okay. The second remark is that we use work of Bachmann-Elmanto-Morrow. To construct the cdh-local version of theorem A, the cdh-local version of Motivic cohomology. So let me say a word about that. So construct cdh-local Motivic complexes denoted by Zi cdh. Okay, so this is a theory which should be the cdh simplification of this theory, and we use this in the definition of Motivic cohomology. But in particular, this will be the cdh simplification of our Motivic cohomology. Okay. Okay, so if I construct such a theory, prove the cdh simplified version of this main theorem. Okay, so the main difference in this theorem is that the Atiyah-Hirzebruch spectral response for the cdh-local Motivic complexes converges not to algebraic K-theory of X, but to homotopy K-theory KH of X. Okay. So there are two ways to think about KH theory. The first one, which is due to Bible, is to see KH theory as the A1 localization of K theory. The second way to look at KH theory is to look at at KH theory as a cdh simplification of K theory, and this is the point of view of Bachmann-Elmanto-Morrow. So to relate these two points of views, like a third remark, so there exists map Motivic cohomology, cdh-local Motivic cohomology. Okay, and we can prove this map. It's an equivalence after A1 localization. So if you enforce A1 invariance on both theories, then they become the same.
Are these seriously seems?
Yes.
Yeah.
Yes. Both of them are.
Yeah.
Even this knowledge. Yeah. Okay, the last remark. Okay, one of the main novelties in working with singular schemes for K theory is that you can see negative K groups, which are non-trivial. Main conjecture of negative K groups of singular varieties. Variable vanishing conjecture, which is now a theorem Kerr-Ström-Tamme. So it states that for X any Noetherian scheme, that the negative K groups vanish below a certain degree depending on the dimension. And strictly less than the dimension of independence, the dimension of X, the K groups vanish. Okay. So we proved, okay, so we would like to see if we can see this information, if this information is reflected in the theory of Motivic cohomology, which is a refinement of that, and indeed it is. So we prove Motivic refinement of that. Which is that the Motivic cohomology groups of X vanish in a certain range. So in weight I, these vanish for n bigger than I plus the dimension of X. So again, if X is not n. Okay. So this is actually a refinement because if you plug this information in the Atiyah-Hirzebruch spectral sequence for Motivic cohomology to K theory, then you recover variable vanishing conjecture.
So you have another proof, or
so the proof is new because these didn't exist before, but it uses the same arguments as in the article of Kerr-Ström, the same techniques.
another question. So you are claiming that even if X is smooth over a field, your complex is not the quasi-isomorphic to the block complex in general.
It should
Not
be
A1.
It should be, but it's not proved.
Ah, okay. Because I was wondering that there is another Atiyah-Hirzebruch spectral sequence. Okay.
Yeah. Okay, so now let me explain the construction of this new theory of Motivic cohomology. Okay, so for this construction, we'd like to plug in some information which is not A1 invariant to get all of the information in algebraic K theory. To do that, we use localizing invariants. More precisely, so we use so-called the Hochschild homology. Indeed by HH of X. Okay, so we fix the quasi-compact quasi-separated scheme X. We use the construction of Motivic cohomology. Okay, so this complex was introduced by Cohn in the 80s. It is equipped with I will not go into the definition of that, but it is equipped with an action of the circle S1. And we use the variance of that. such as so-called negative cyclic homology, which is finer invariant and closer to K theory. So denoted by HC minus of X and defined in terms of Rothschild homology by just taking the fixed points for the S1 action. This is the homotopy fixed points, HS1. Okay, so we want to use that. So this theory is well behaved in characteristic 0, but in characteristic P or in mixed characteristic, we want also more refined invariant called the topological cyclic homology. Denoted by TC of X. Okay, so I will not say the definition of TC of X, but just mention that these are related by Gartland square. Yes, first we have topological cyclic homology of X, which can be recoupled from the information first of all of the T completions of TC of X. So we denote them by TC of X dt. So we just T completion of that. And also some information from that T0, so HC of the rationalization of X. And we glue these two informations along some sort of p-adic rigid analytic invariant. So we take our field homology, then we Phi complete, then we invert P, then we take the fixed point for the S1 action. So this is really a term which is close to this one. Okay, so this is a Cartesian square, meaning that all of the information TC of X can be recovered from these three terms. Okay. So now the construction goes as follows. First, we use the work of Atiyah. So it's a theorem, and so we construct a filtration. So it's related to the so-called edge-car filtration for Hochschild constant and Rosenberg. So this is a filtration on this term with gradients. Some derived Durham cohomology. So this is really the ice piece of Hodge complete derived Durham cohomology. The rationalization of X. Shift. Okay, so this is Hodge complete derived Durham cohomology. It was first introduced by Illuzi and then studied again about 10 years ago by Bhatt. Okay. Okay, so we have a filtration here, and we also have a filtration on this term. More precisely, as the work of Bhatt-Morrow-Scholze. Similarly, they construct the filtration. Which we'll call the BMS filtration on this term. With gradients. Syntomic homology of X. Okay. So we have two filtrations on this term and this term. And now the first step of the construction is to construct a filtration here, which is compatible with the other two. Step one of the construction. Define a new filtration system. Which is in spirit similar to the H-car filtration of Fantio. And with gradients, analog of derived cohomology. With for the p-adic rigid and magnetic. Generic fiber. X. Okay, so it's like a formal statement about that, you need to use a condenser. Okay, and you also need, after having this definition, to prove that this is compatible with these two maps. Okay, meaning that the two maps from HC minus to this, from TCP completed to that, can be refined into filtered maps. So compatible. With the other two filtration. Okay.
For what X do you need to do this?
qcqs key.
All Qs?
Yes. Yes. Okay, so once you do that, in the step.
Another quick question, in this case, I mean, does this ZPI sin only depend on the peak completion of X?
Yes, it does. Yeah, just a notation, but yeah. Okay, so step two, we define the filtration on TC of X, just pulling back these three filtrations which are compatible. Equip TC of X. With a pullback filtration. So in that class, this defines a new homology theory. You can call it ZITC of X. You can call the graded pieces of that. Okay, so now we have that. We need to relate the history to algebraic K-theory and to actually define a filtration on algebraic K-theory of X. Okay, to do that, we use a deep result in the algebraic K-theory. Use the Polemic Cartesian square. To Kerström terme. And put together with the result of Land terme. Okay, so which says the following. So we have the algebraic K-theory of X. We have the so-called cyclotomic trace map, which goes from K-theory of X to TC of X. This is usually where we use TC, so topological cyclic homology, to study algebraic K-theory. And another approximation of K-theory is this variable, the homotopy K-theory, KH of X. Okay, and the result is that having these two informations is enough to capture all of the information from algebraic K-theory. More precisely, so K-theory can be seen as a cdh-ification of K-theory. This is the result of Kerström terme. You can do all of these two informations along the cdh-ification of TC of X. Okay. This is the Cartesian square. Okay, so to define the filtration in K-theory of X, we do the same as before. So we define three filtrations on the other terms, and we just pull back. First, this term we actually have a filtration by step 2. Okay. Then on the bottom right term, we also have a filtration formally by taking the cdh-location of the previous one. Then evaluate x. Okay. You see also term on ah(x). This is the work as what I was mentioning before. These are Bhatt-Morrow-Scholze. These cdh-local Motivic complexes of E4. Okay, now we have all of these three filtrations. So it is not obvious to see, okay, for this map, this is a filtered map by definition. This becomes a filtered map by definition. But for this map, it is absolutely non-trivial to prove that you can refine this map as a filtered map using these two filtrations. But you can actually do that. And, last step of the definition. Equip the K-theory of X with the pullback filtration. After proving that these are compatible. And again, you can denote graded time this theory of Motivic cohomology. Just a homological shift. Okay, so this is it for the definition of Motivic cohomology. So going back to theorem A, the Atiyah-Hirzebruch spectral sequence is just a direct consequence of the definition. We constructed the filtration on algebraic K-theory. So we just take the spectral sequence associated to this filtration. For the Bhatt-Morrow-Scholze non-comparison map, this actually factors, okay, so this was taken as a black box, so the cdh-local theory, but it is constructed in terms of the classical theory of Motivic cohomology in the smooth case. And so it has a map to the étale cohomology, a Bhatt-Morrow-Scholze non-comparison map. And so the Bhatt-Morrow-Scholze non-comparison map for our theory factors through the cdh-local theory. Okay, so I'll just say that for the main theorem. Now let me make an example to illustrate this theory for on a specific non-smooth schemes on singular scheme in mixed characteristic.
Ask, is it annoying? Is completeness and exhaustion like annoying to show, or?
So it's not obvious, but okay, you can play around with the definition and prove the exhaustiveness by proving that it is n-indexed, which is not obvious because you need to play around with the Hodge filtration and everything. So it cancels out with cdh justification, but it's not true on all of these three terms. It's true on this one and on the fiber of this one. And for the completeness, it is true for finite dimensional schemes, or maybe finite valuative dimension. Yeah.
So you're saying that for I less than 0, this ZI is 0.
Yes. Yes, it is. Okay. Example. Okay, so I will take the following scheme. So this is an affine scheme of a Z given by truncated polynomials like that, where E positive integer. Okay, so for E is equal to 1, so I would like to compute the Motivic cohomology groups of this ring. For E is equal to 1, this would be the Motivic cohomology of Z, which would be a refinement of the K-theory of Z, which is hard to compute. So instead, let me do the following. So I define the relative Motivic cohomology. Relative to this ideal T, to be the fiber from Motivic cohomology of this ring to the Motivic cohomology of Z. Is for any I greater than 0. So to compute these, going back to the definition is in terms, in particular, of derived cohomology and in terms of syntomic cohomology. So syntomic cohomology, I didn't say that, it can be defined in terms of prismatic cohomology, roughly as Frobenius eigenspaces and prismatic cohomology. So the idea now is to do computation in prismatic cohomology and in derived cohomology, and to deduce from that computations of Motivic cohomology. This is what we do, so calculations prismatic derived cohomology. Simplify, going through all of these definitions, that can actually have a computation of the Motivic cohomology groups of the ring. Define not okay, so three cases. First one is for n is equal to 0. So this is a group, the finite group, or for the EI factorial factor I factorial to E minus 2. Okay, so this is for n is equal to 0. For n is equal to 1, this is a free abelian group, or for the E minus 1. And for any other n, this is 0. Okay, so in particular, we have few terms in the Atiyah-Hirzebruch spectral sequence. So this implies similar calculations of on the bytes.
Sorry, in first part, it's a group of this order, or
Yeah, sorry. Yeah, yes.
but it's not known the simple structure.
It's not under structure.
Uh-huh.
We just have the cardinality here. Yes, right. Okay. So it's a calculation of angle light, Gerhardt, Hirzebruch. Also relative K groups of this same ring. Relative K groups being defined in the same way. Okay. So let me mention briefly another example, which is of more recent interest, interest is the calculations of the K groups of Z mod P to the N. It is also possible to exploit the information of in these computations of Antio, Krause, and Nicolaus of syntomic cohomology of Z mod P to the N, and to deduce similar computations of the Motivic cohomology groups of Z mod P to the N, which is the direct refinement of the calculations of the K groups. Okay. Let me now discuss some periodic information. Okay, sorry. Maybe the newest information of this theory of Motivic cohomology is really the periodic Motivic cohomology of periodic rings or periodic schemes. Let me mention some results in this direction too. Okay, so this is formulated over a perfected ring. So this is the case. Perfected base. So 6 P a prime number and V is often free. Factoid valuation ring. So for instance, you can think about taking the integers, adding all of the people roots of unity, and then completing, or also in the ring of integers of the periodic complex numbers. So now let me mention the fact, which is due to Bhatt-Scholze for I is equal to 0. Into Bhatt-Scholze for general I. Stating that for any ring R and a non-negative integer I, there is a comparison map. So this statement will be to compare the syntomic cohomology appearing in the definition of Motivic cohomology to étale cohomology. So there is a natural syntomic étale comparison map. So it's a finite coefficients so going from syntomic cohomology R to the étale cohomology of the generic fiber of so now the idea is that we like to have a control of syntomic cohomology in terms of étale cohomology of the generic fiber. So this is the following result. This looks like the Bell-Insel-Nash comparison of the beginning. So let me denote this comparison map as star. So the fiber of this map is in degrees at least I plus 1. So in two cases. First, so this is the result due to Bhatt-Matthew. But when R is regular notated ring, okay. then the result of interest for us will be the following. So it's a non-Noetherian analog of the result of Bhatt and Matthew. The idea is that we like a similar result for valuation rings, with the intuition that valuation rings should behave as filtered columnists of regular rings. That's if you believe in a sort of resolution of singularities. And the result is the following. So the same is true. Valuation ring extension of the perfectoid base that we fixed, so of this valuation ring V. Okay, so we'll use this result in the following way. So in the definition of Motivic cohomology, we had a lot of cdh justifications, and valuation rings or Held-Zillion valuation rings are local rings in the cdh topology. So the idea is to use this result to control the syntomic cohomology. So that is in terms of total cohomology, which is better understood. So cdh locally and over this perfectoid base V. Okay. So we can do several things with some, but let me mention one result to finish. So this is to complete the first theorem I stated, but this time with P, which is not invariant in your scheme. This is only in the case of a perfectoid. So for any smooth scheme X of a spec V, and a weight I. So from theorem A, we had the comparison map to total cohomology. So we have Bellin-Samuelson-Lamb comparison map.
Or in a smooth scheme,
Yes.
I had no theorem scheme, so that was strange, but sorry.
So it goes from a Motivic cohomology of X modulo P to the total cohomology of periodic generalized library of X. Okay. So we have the same result as in the elliptic case, spider. Is at least A plus 1. How much time do I have left?
12 minutes?
Okay. Okay.
But can I ask, are you assuming R is complete, or now do you mean the other version of syntomic cohomology?
Okay, yeah, sorry, I cheated a little bit, so I should have put that. Okay, yeah. Okay, so let me sketch a few proofs of these two results. So first, for this result, so the idea is playing. So okay, so we know the same result in characteristic phi due to no, that's not in characteristic. We have construct sort of tilt of this valuation ring R. Where the tilt of the perfect valuation ring V, so it is in characteristic P. Formation V. Okay. We use some result on some extension of characteristic P evaluation rings. By Gaber and Bhatt-Morrow-Scholze. Okay, and this is the control. Okay, so this gives you some information on the cotangent complex of extension of valuation rings in characteristic P. And the idea is to go from this information to actually some control on the relative prismatic cohomology of this extension of valuation ring in mixed characteristic. It is to do that like that. And okay, and then you go from the information on prismatic cohomology to the information on syntomic cohomology, because the syntomic cohomology is related to prismatic cohomology. Okay. Yes. Okay. So proof of theorem C. So the idea is to go back to the definition of Motivic cohomology. So this is in terms of the cdh-local Motivic cohomology of X, the syntomic cohomology of X, and the cdh-local, so cdh-shified syntomic cohomology of X. More essentially, we have things. So okay, so this is this term, so Motivic cohomology modulo P. So there is a Cartesian square. It's syntomic cohomology X. So cdh-shification of syntomic cohomology X. And it's a cdh-local Motivic cohomology of X. It's the P coefficient. It is a Cartesian square. Then, okay, so we have some control on the syntomic cohomology of X. So this is where we use the hypothesis of smoothness of X. Control syntomic cohomology of X. So this is a result of Bhatt-Morrow-Scholze. Okay, and then the new input is to actually control the other two terms, which are cdh sheaves, in terms of the theorem B. So this result in valuation. example. So first, this is what I said before. So cdh-local syntomic cohomology. cdh-local Motivic Cohomology. Again, in terms of catalog cohomology. This theorem on valuation layers. Okay, let me stop.
Hey, any questions for the speaker?
So in this rigid generic fiber thing, so you prove some analog of a theorem of goodwill in that situation.
Yes.
Can you tell us what is the analog?
What is the analog theorem? Yeah. So, okay, the theorem of goodwill is that, I understood the question at least, is that in characteristic 0, we have that schemes Q. For X, Q, we have that HP, so periodic cyclic quantity. It's the same as the cdh-location of periodic cyclic quantity. The analog of that within analytic setting will be that for any scheme, okay, so first we rephrase this result by saying that for any scheme X, have a name. So just a information. And the idea now is to say that for any X, then you have that you take our shield homology, you P complete, you embed P, this is QP equation. Then you take the tape construction. This will be the same as cdh equation. So here, we take QP equations, Tx1, apply to us. So this could be the analog, and this is what's good, yes.
And is condensed mathematics used to do that?
So you can prove this in several ways. One of them is in terms of condensed math, and it's a reformulation of the usual goodwill argument from the 80s, which works actually in any abelian category context. And so you can reformulate that in terms of the category of the abelian category of solid modules over QP. So there is a proof like that. There is also an elementary proof without that. Yes.
Do you think of these motivic complexes as a functor of a commutative ring?
Yes.
Is that functor left conextended from smooth Z algebras?
It is not. It is not. If you did that, you would see only the non-negative K groups in K theory. So this is the motivation to actually add some information to see this negative K groups.
In this example of Motivic cohomology of Z of T quotient by T to the power E, if you replace Z with some other ring over Z, how does the answer change?
So I think it works for something which is formally étal over Z.
No, but if I don't know, take polynomial ring.
But any ring now it doesn't work the same. So the idea here is that it is kind of easy to compute because it's low dimensional. So if you had higher dimensions, you will get more non-trivial groups.
Okay.
Yeah.
So it's not left con extended, but you expect that it's left con extended and then sheavified.
Yes, indeed, it should be left can extension from the smooth case, and then pro-cdh sheavification, which is this pro-cdh topology introduced by Kelly and Saito about a month ago.
Syrian.
What?
Syrian.
Noetherian, yes, in the Noetherian case.
Sorry, so this is some topology where nilpotents are not destroyed?
Yes, actually, yeah. So this is related to to the pro-excision of algebraic case theory.
Is it possible that in some kind of cohomological range, it is left-Kahn extended?
Yeah, it should be definitely, but it's hard to.
In theory, it's okay in non-negative degrees.
Yes, so for the scheme, it is true. It's proved by Elmanto-Morrow. In with less than I, or at most I, in white I. But it uses the Gaston conjecture. For no, there's no proof in mixed characteristic of the Gaston conjecture or just of this. But it is appropriate.
So, sorry, say again. So in mixed characteristic, do you get similar results?
No, at least not for them. There should be some result like that, but it's not true.
These integral syntomic complexes left-Kahn extended, or are they also not?
So yes, there are left connections from the polynomial rings actually. Yeah.
So in this construction, what sort of control do you get from definition theory?
So it's first on the contour complex. Okay, so precisely you get that the reduction modulo P of your morphism satisfies the Cartesian morphism. And then you can control the Dirac-Delorme cohomology of the extension and arithmetic cohomology.
So the cotangent complex in particular is free.
It's discrete, and more than that, it satisfies the Cartesian morphism. So it's
But is it a finite projective module or is it infinite?
so it's not finite projective, but it's a flat module in degree 0.
I guess I'm just trying to understand the definition theory comment.
It's just to construct this thing. So first you start from the reduction modulo P, and then if you have enough information on the cotangent complex of that, then you can lift step by step to something which is a valuation ring. Because R mod P is not a valuation ring, but if you deform, you can deform it modulo P tilt over something.
Would you not run into an obstruction group which is like X2 out of the flat module?
Absolutely, yeah. And you prove that this obstruction is 0.
You shut that zero.
Yeah, exactly. Yeah. That's the group. Yeah.
Okay. Well, if there are no other questions, like, thanks again.